Good morning, children. Today let us see the important concepts of thermodynamics, and this is in continuation with the previous concepts of thermodynamics. In this class, we are going to discuss standard enthalpy of combustion, standard enthalpy of atomization, standard enthalpy of solution. This follows first law of thermodynamics. And after first law of thermodynamics, let us see Hess's law of constant heat summation. Otherwise, simply you can write Hess's law of constant, let it be heat summation. If time permits, we will move to the other topic, that is entropy. If time permits. Okay, these are some of the important topics which we are going to discuss now. First topic which I am going to teach now is standard enthalpy of combustion. Standard enthalpy of combustion. Combustion means burning. Standard means known. That means temperature and pressure. Right? So standard enthalpy of combustion refers to heat change accompanied by a burning reaction in standard conditions. This is the concept. Right? Standard conditions means already it was taught. What should be the fixed temperature and pressure. So this is nothing but heat change or enthalpy change accompanied by a reaction or change in enthalpy accompanied by a reaction where 1 mole of a substance is subjected to combustion completely. Means that substance should have been burned in that change of the reaction completely. Quantity of the substance should be 1 mole. Right? And conditions are known. Change in enthalpy accompanied by a reaction wherein 1 mole of a substance is subjected to combustion completely in standard conditions. This is the concept. Now, we will take one example wherein 1 mole of glucose is taken. And when it is subjected to combustion, means in presence of oxygen, because it is supporter of combustion, not burning. Then we will get carbon dioxide, CO2 and H2O. And at the same time, 2802 kilojoules amount of energy is released. So glucose is C6, H12, O6. Right? And this is subjected to burning. Supporter of burning is oxygen. Right? Then we will get carbon dioxide in this reaction, H2O, right? And standard enthalpy of combustion is symbolically represented by delta C H naught. This is equal to minus 2802 kilojoules per mole. This much amount of energy is released in this reaction. Okay. Here 6 carbon atoms we have, so 6 CO2. Here 12 hydrogen atoms. Here we have 2, so multiplied by. Now 12 oxygen atoms and 6. 18 oxygen atoms. Here we have 6. 12 more required. So already 2 is there, multiplied by 6. That's all. So this is an example. Many examples are given in your textbook. You can go for any example. It can be LPG. That also undergoes combustion very easily because it is highly flammable gas. Fine. Now we are moving to the second concept, that is standard enthalpy of atomization. Standard enthalpy of atomization. A-T-I-O-N, formation. Atomization means formation of atoms from the molecule, right? So standard enthalpy of atomization means enthalpy change. Enthalpy means energy. Change in energy associated with a reaction wherein 1 mole of a substance is converted completely into atoms in standard conditions is known as standard enthalpy of atomization. So you can write change in enthalpy means energy accompanied by a reaction where 1 mole of a substance is completely converted into atoms in standard conditions. This is the definition or concept. Right. Now let us see example for this. If you take 1 mole of hydrogen gas means H2. So 1 mole of hydrogen gas weighs 2 grams. Right? When 2 grams of hydrogen gas is taken and it is subjected to atomization process, then we will get 2 moles of hydrogen atoms, 2H, in standard conditions. And when this process takes place, 485 kilojoules amount of energy is absorbed. So this means the energy that is being released in this process is accompanied by plus sign, means it is endothermic. Unlike enthalpy of combustion, wherein minus sign is there, means energy is released there. So here, best example for this, as I told you, hydrogen gas we can take. Here physical states, if we want, we can write. Okay, and this is converted into 2 moles of hydrogen atoms. So physical states, if we want, we can write. And standard enthalpy of atomization is symbolically represented by delta A for atomization, H for enthalpy. And if you write superscript 0, that stands for standard. So this is plus 485 kilojoules per mole. Means when 2 grams of hydrogen gas is subjected to atomization, this much amount of energy is taken by the system. That is 2 grams of hydrogen. In this reaction also, if physical states you want, you can write oxygen gas, glucose is solid. C6H12O6 is glucose. Okay. Now let us see the third important concept, that is standard enthalpy of solution. Number 3, standard enthalpy of solution. Enthalpy means energy, as usually it is known. Solution means a process wherein particular amount of solute is dissolved in the solvent, thereby to form what you call the binary solution. Here solute should be completely miscible in water. So according to the concept, standard enthalpy of solution, change in energy accompanied by a reaction wherein 1 mole of a solute is completely dissolved in the required amount of, or the sufficient amount of solvent. So in this case also, solute to undergo miscibility with water, energy is required to be absorbed. So standard enthalpy of solution is accompanied by a positive sign. So concept is like this: change in enthalpy accompanied by a reaction. Accompanied by a reaction wherein 1 mole of a solute, the term miscible solute in solvent, 1 mole of a solute is dissolved to form a solution. So dissolved means solvent. It is to be dissolved in solvent. Fine. Now let us see what is that solute. In this example, we can take sodium chloride as solute. To this, we will add water. That means aqueous medium we are going to add. Okay, and sodium chloride is solid. Okay, in place of aqueous medium, we can write water also. Then it gives rise to aqueous sodium chloride solution. And here standard enthalpy of solution is symbolically represented by delta SOL H naught. This is equal to plus 3.9 kilojoules per mole. This is the amount of energy required to make the binary solution. That's about standard enthalpy of solution. So change in enthalpy accompanied by a reaction wherein 1 mole of a solute is dissolved to form a solution in standard conditions. Next, first law of thermodynamics. This is nothing but law of conservation of energy. So whenever a system undergoes a change or change in enthalpy or energy accompanied by a reaction wherein a particular system is involved, that system may be composed of only one reactant consisting of or more than one reactant. Net change in the energy remains always constant. Means total energy of the system will not be destroyed. Right? Extra energy cannot be created from that system. So always the energy remains constant. This is nothing but first law of thermodynamics. First law of thermodynamics. So this is nothing but law of conservation of energy. Means energy is always conserved. It is not created and it's not destroyed. That is the meaning of law of conservation of energy. This is nothing but first law of thermodynamics. This is one important concept. Yes, children. Now we will move to another important concept. In this concept, we are going to see total change in enthalpy or energy accompanied by a reaction when it occurs in a single step. Sometimes same reaction occurs in more than one step. When reaction occurs in many steps, then if we add all the changes in enthalpies of those steps, if we add, then the total change in enthalpy which we are going to get will be equal to the total change in enthalpy accompanied by the same reaction when it occurs in one step. So that is nothing but law of or Hess's law of constant heat summation. Hess's law of constant heat summation. So why here heat is written is it is nothing but energy and it remains same whether that reaction is going to take place in single step or in multiple steps, means in more than one step. Now let us see best example for this law is combustion of carbon. When carbon is subjected to combustion in sufficient amount of oxygen, then minus 393.5 kilojoules amount of energy is released. This is single step and that is delta H naught value. Right? Next point. If this step occurs in if this reaction occurs in two steps, Imagine sufficient amount of oxygen is not there. Then in first step, when carbon is subjected to bonding, it gives rise to carbon monoxide. And in this case, in between carbon and oxygen, bonds are made, so energy is released and it is equal to minus 110.5 kilojoules amount of energy is released. Next, that is one step. In second step, thus formed carbon monoxide once again undergoes oxidation, reacts with oxygen, thereby to form carbon dioxide gas. Then 283 kilojoules amount of energy is absorbed. Now, in these two steps, the total amount of energy released, if we add, it will matches with the total amount of energy released when carbon is completely burnt in sufficient amount of energy, that is minus 393.5 kilojoules. This is the explanatory part. Now, let us see whole thing in the form of equations. So here carbon is solid when it combines with sufficient amount of oxygen during combustion. So we have to give energy, otherwise these two will not be combined. As a result, we will get carbon dioxide gas. In this reaction, here carbon is subjected to combustion. So we can write delta C H0 or delta H0 is equal to minus 393.5 kilojoules per mole. And this has taken place in single step. When the same reaction occurs in two steps, like carbon solid will combine with insufficient amount of oxygen, a half mole 2. Otherwise, we can write 2C plus mole 2. That gives rise to 2CO. Otherwise, C plus half mole 2, which gives rise to CO, that is carbon monoxide, is a gas. And in this reaction is taking place in two steps. This is step 1. So we write delta 1 H0. This is equal to minus 110.5 kilojoules per mole. This much amount of energy is released. In second step, what happens is, so formed carbon monoxide gas combines with oxygen chemically. As a result, we will get carbon dioxide gas. And in this reaction, the amount of energy accompanied is delta 2 H0 is equal to 283 kilojoules per mole. And according to Hess, yes, according to Hess's law, we can write in this way. According to Hess's law, delta H naught is equal to delta 1 H naught plus delta 2 H naught. Right? So let this be equation number 1, this is equation number 2, equation number 3, that way. Right? So here we are clubbing equation number 2 and 3. So delta H naught value is equal to minus 393.5 kilojoules. Delta 1 H naught is minus 110.5 kilojoules and delta 2 H naught is equal to 283.0 and this is equal to minus 393.5. Right? This is nothing but what do you call Hess's law. This is according to Hess's law. So kilojoules per mole. Right? Now we'll move to a new concept, and that new concept is nothing but entropy. What is meant by entropy and what is its relation with spontaneity? This is what we are going to. So before going to start entropy, let me teach what is meant by spontaneous process. Process means it's a change, spontaneous reaction, spontaneity, right? Spontaneous process. All these refers to same. So whenever a particular change occurs on its own, right, in the nature, that is said to be spontaneous reaction. Like, imagine a body which is at a higher temperature. Degree of hotness of that body or system is more. So when it is there in the nature, from that, imagine surrounding is at lower temperature. Then from that body or the system which is accompanied by large amount of heat energy. So heat energy passes or travels from that system to the surrounding which is at lower temperature. This is spontaneous reaction. Number 2, naphthalene balls. They are in solid form. Generally they are kept in toilet rooms. 2, what do you call, repel moths or insects. And these naphthalene balls are also kept in between the clothes, costly clothes, so that moths cannot enter and they cannot make holes. Right? That solid naphthalene ball enters into gaseous form on its own. So that is also a spontaneous reaction. Now let us see what they call entropy. This is symbolically represented by the letter S. Entropy of any system refers to degree of randomness. Is nothing but degree, means quantity or amount of randomness of a system is called entropy. And entropy is a state function because entropy depends on heat energy. Right? So entropy of a system depends. Since it depends on energy, so like internal energy and enthalpy, it is a state function. Right? Imagine a balloon which is inflated. Right? Balloon is there in my hand I inflated it by blowing air into it, and then I tied the open end of that balloon with thread. So I am holding that balloon in one hand and a needle in other hand. With the help of that needle, I will make pinhole on the balloon. Then the air present in that balloon will come out with his sound. So the phenomenon wherein air comes out through a pinhole is known as effusion. E-F-F-U-S-I-O-N. Diffusion is different again. Right? Now, the thing is, as long as air is there in the balloon, all the molecules are lying very close to each other, right? And degree of randomness means kinetic energy of those molecules is restricted very much within that balloon. But when a small pinhole is made, that air or the molecules present in that air will come out through that pinhole and will spread in all the available directions in the surrounding. Means amount of randomness is increased, kinetic energy of the molecules increased, and those molecules started moving or flowing in all the available directions. Means entropy is increasing. Right? Next. If you take water in a container, imagine, because of association properties, all the molecules are closely lying with each other. But when we start giving energy to it, when boiling begins, from the surface of water, the molecules of water begins to evaporate. Those molecules begin to move in all the available directions. So their physical state is changing from liquid to vapor, right? That is accompanied by increase in entropy, and change in entropy is symbolically represented by the letter delta S, and this is inversely proportionate to absolute temperature and directly proportionate to the amount of heat energy, change in amount of heat energy accompanied by a reversible reaction. So it can be written like this: Q reverse, or EV stands for reversible reaction. Right? Now, in this reaction, delta, we can write here delta T. Now, if you take entropy of entire universe, it will be equal to, because in the universe we have system, number 2 surrounding, right? So the total change in entropy, that can be written in this way: delta S T. In some books TOTL is written, it can be written in the term. So total change in entropy of the universe is equal to change in entropy of the system plus change in entropy of the surrounding. Right? Let this be equation number 1, the other one is 2, where delta S total stands for total change in entropy or universe. Right? Here if you want you can add universe, otherwise that part you can remove. Total change in entropy of universe, and delta S stands for change in entropy of a system, and delta S surrounding, SUR or SUR, okay, let it be SUR, is equal to change in entropy or surrounding. Children, in this expressions, in the first expression if you take, we have change in entropy, change in energy accompanied by irreversible reaction and change in absolute temperature. Right? Out of these three, if we know any two variables, the third unknown one can be calculated. Similarly, in the case of equation 2. So that's about entropy and the expressions related to entropy. Thank you, children.